Hello everyone, welcome back. In the last lecture we looked at how to create magnetic response and how the metamaterial designs have evolved. So we focused primarily on what is known as split ring resonator, and we saw that as you shrink the sizes of the split rings, the fabrication becomes much more challenging and it's very difficult to scale up the magnetic response up to the visible and near ear frequencies. So in this lecture we will look at alternative structures and think about how to achieve the magnetic response. So there was a theoretical proposal, I think in the late 90s or early 2000s, wherein a pair of nanorods, this is a pair of nanorods here, pair of nanorods exhibits magnetic response. The reason it exhibits a magnetic response is, if you think about this, the magnetic field is in this direction, in the perpendicular to this axis of the nanorods, and then you can have a circulating current going in these two rods. So in this fashion there can be circulating current. So you'll have conduction current and then the displacement current at the gaps. So basically this circulating current will give you the magnetic response. So this was a proposal that was done way back. Okay, so basically this displacement current loop gives rise to magnetic response, and magnetic field is confined between the rods. So and people have done simulations and showed that this can actually be used even up to near ear frequencies. So but the problem is, if you have nanorods and individual each, this is a meta atom having a magnetic response, and then I can arrange them in a periodic lattice and I can create a metamaterial, right? But it turns out that creating nanorods like this is challenging. When we actually try to fabricate them, it's very difficult to get two rods like this, especially in the nanometer scale dimension, 30-40 nanometers dimensions which we want. It becomes extremely challenging, and that's why people end up fabricating things like these strips on the right side. This is a more, I would say, a fabricatable, okay, I don't know if that's a word, but a structure wherein instead of having two rods which are like this, you actually create you take a lithography process, you actually perform what is known as a lithography process, wherein you apply a photoresist and then you make a hole where you want a metal to be, deposit metal, and then deposit alumina, and then deposit silver again in the metal. So you can create a structure like this, and it ends up in this form. It will never be a proper straight line, but it ends up in the trapezoidal form. So this is a metamaterial that the researchers at Purdue have investigated. And okay, instead of going to the strips of these nanorods, initially first they looked at what happens when you have a grating consisting of these metallic structures. So again, in this case, now you can also have magnetic field in this way, and you can have circulating current, but this is semi-infinite. If you have such a scenario, you have to consider magnetic field only in the axis of the strip. Okay, so these are basically strips of metals with Al2O3 spacer. So it's like a grating. Okay, when you have such a scenario and your magnetic field is along the strip, then you will have a circulating current. So your circulating current will go between these metals like this, and you will have a strong confinement of magnetic field between the gaps, in the gap. All right. So this can confinement of magnetic field in the gap. Okay, you can have such a scenario. So what happens is, in this case, I can look at a structure which is fabricatable, and then this is the actual structure which is fabricated. So you see that it's not straight lines, it's sort of trapezoidal, and that's what an AFM image also shows you. And if you have such a structure, you can have excitations in two ways. One is the TM incidence. When I say TM incidence, essentially I mean, let's say if this is my cross section, I'm looking at the side view of this. My incident and reflected waves are going to be like this. So if a magnetic field is transverse, that means TM is magnetic field is along the strip. Okay, when I have magnetic field H along the strip, and T is E along the strip. So I can look at these structures, and you'll see that two types of resonances are excited. Okay, when your magnetic field is along the strip, we talked about the circulating displacement current, and that is what is being shown here. So you see the arrows represent the displacement current, and you see that the displacement current is going in this circular fashion, essentially meaning that there is a strong confined magnetic field, which is what you see here. This is basically the blue region. This is a magnetic field. I would say this is confined magnetic field. Between this is basically going to be my metal, Ag, this is Ag, and in between you have alumina. The reason alumina is chosen is that alumina has a slightly higher dielectric constant compared to silicon dioxide, so it will have much better confinement. That's why alumina is chosen. So you have silver and two metals, and in between there is a so this is a magnetic response. And when you have just electric field along the in the T, you can also add this occurs at one particular wavelength. Okay, sorry, occurs at a lambda depending on size parameters. Okay. In addition to this magnetic resonance, at a different wavelength, you can also have electric resonance. Occurs, let's say, at lambda E. This I'll call it as lambda M magnetic response. So the lambda E, lambda M never going to be equal because the way the geometry is. And in this case, at the electric resonance, you see that the field lines or the currents are predominantly in one direction, and there's a small circulating component, and that's actually fairly weak. You see the red here, red corresponds to roughly about 1. In this case, blue corresponds to about 7. So you see the magnetic field confinement is much weaker at this, and this is predominantly electric resonance. So if you go and look at these papers in the bottom, you'll actually see the spectrums, and then you'll see that this structure has a very strong magnetic response, and actually they'll identify what wavelength it occurs. But what I wanted to emphasize is the dramatic difference that you see when you look at these structures. You fabricate these strips or gratings in a periodic array, and then look at them in TE and TM polarizations. So the bright field microscope image is shown here. So these are different arrays consisting of different geometrical parameters, width, length, thickness, and so on. They varied a range of parameters, and you see the same exact strips under TE incidence and TM incidence. In TM case, you see very bright colors that come, and the colors are changing. The reason the colors are changing is the resonance is shifting, and for example, this is reddish region, this is more bluish region. So as you make the dimension smaller and you move the magnetic resonance to the lower wavelengths, you see a bluish tinge appearing, and green, and so on. So there's a strong magnetic response that can be tuned across the visible frequencies. And previously we saw that this magnetic response was never going below 3 microns. So with this sort of a strip geometry, we are getting magnetic response down to visible wavelengths. But if you look at the TE resonance is not really that dependent on sizes. Essentially, it is a plasmonic resonance in the metals, and that's not very strongly dependent. In this case, this is a localized surface plasmon, and that is not very strongly dependent on the size, and that's why you see the colors of these structures are not really that much significantly varying when I look at the TE response. So with this, it was possible to actually get magnetic response. But we are not happy with magnetic response. We want to get to a negative index material. That means we want to overlap the electric and magnetic response in such a way that you get a negative index. And that was first achieved at near IR frequencies by, again, Professor Shalaiv's group at Purdue. And they showed that if you have this pair of strips and you make a periodic array of these strips and you make a metamaterial, so you see this periodic, it's a lattice that is created of these strips, and the size of the strips is quite small, and the periodicity is, the size is given here, and then there's some periodicity. I don't remember how much, but you can go and look at their paper. This is an optics latest paper in 2005, I believe. All right. So if you see that and you analyze the response of it, what you will see is they're able to show that this is a refractive index, and over at the telecommunications frequencies, you are able to get actually a negative index. At lambda equal to 1.5 micrometers. So you see the evolution. So this was, I think, in 2005. So in 2001, the first demonstration happened at RF frequencies. 2004 already we came to terahertz, 10 terahertz, and also 100 terahertz. No, 1 terahertz and 100 terahertz. And by 2005-6 time frame, already the negative index was shown at near air frequencies. And of course, the next step was what happens, how can we do it at visible frequencies? So this was a very nice, intense game that was going on in those periods, very exciting time for metamaterials, wherein various groups were trying to demonstrate, negative index. Okay, so this is the example of negative index at visible frequencies. So in this case, we saw that if you have a strip like this, it exhibits a magnetic response. But if you have a perpendicular incidence, it exhibits a electric response, but it is not actually resonant. So what if you combine these two? So we saw in the previous case here that if I have this resonant response in the TM polarization, but TE there is no resonant response. It's a non-resonant, right? So now if I combine them and appropriately design a structure, and we end up what is known as this fishnet structure here, essentially saying that you have these two strips which are overlapping with each other. So you have a net kind of a structure. This is a fishnet structure, and you have the metal, dielectric, and metal again. So metal, dielectric, and metal again. When you have such a structure, and you can actually get magnetic or negative index at visible frequencies. Okay, but it's extremely challenging, and it turned out that the losses now, the size of the structure has become very, very small, and the losses were quite high. So it was not possible to actually demonstrate negative index with just passive materials. So they had to infiltrate this with dyes and then provide gain. We'll actually talk about this dyes and gain in the next week. But essentially you have to fill up a dye so that it provides some gain, and with that they were able to show. The result is what is shown here. So you look at the multiple graphs. So what you see is without let's say this solid line is with pump, and dashed line is without pump. So basically this is absorption. So there's a strong absorption in this material, but the moment you add some dye and then pump it, you see the absorption is reducing. And the interesting part is the negative index. So this is without pump. I see that the index is just slightly lower, but it's not really negative. So I'll put it in blue. Without pump, index is not negative. The big problem there is the loss. The loss was high, so you're not getting negative index. So, but if you pump it, you see here in the small frequency range, index is negative. Okay, so they were able to demonstrate negative refractive index in the range of 720 to 760 nanometers. And this was one of the remarkable demonstrations. I was personally there around the time this was finishing, and it was quite intense experimental effort to actually show it. It was not that easy. You might say, why should we care about all this? You showed me that straw bends in a different way if you have a negative index material. So why should I care? Okay, what are the applications of having this negative index? And I briefly alluded to that when I said that if you have waves which are bending in arbitrary waves which are bending in arbitrary directions, you can create stealth, right? Stealth, for aircrafts and so on. I said, yeah, that's one of the applications. But in addition, there was also another interesting example, or rather, proposal that was done by Professor John Pendry, Sir John Pendry out of Imperial College, and that captured attention of people, and the whole community tried to realize that. And that was what is known as a perfect lens. So if you look at any optical lenses, like for example the one that I am wearing, these are curved surfaces, and they are meant to actually introduce a certain phase delay and then correct the focus the light at a particular point, in this case on my retina, right? And similarly, any lenses, the camera lenses are all curved because they have to focus the light at a particular point. So that's a traditional lens. That is what is shown here on the top, and it also creates an inverted image. what Sir John Pendry said in 2000, this was a remarkable paper, and if any student is there, I would ask them to just read this paper, because he writes papers very nicely. I mean, it's an amazing skill. So when you read this paper, you'll really appreciate how papers can be written in a way that everybody can understand. So of course you need some amount of background, but I think with the background that we have in this course, I'm sure you'll be able to understand the paper. So some parts of the paper at least. So now what he said was, you take a negative index medium. Okay. So if I have a pure negative index medium like this, NIM can act as a perfect lens. This was his claim that was really remarkable, and people paid attention to that. What he said was, let's say you have a positive index material, air, and then you create some sort of negative index material of, let's say, some thickness D here. This is my thickness D. If I have such a scenario, and what I can do is I can put an object, close to the perfect lens. Let me say this distance F. At a distance F, I'll place this. If I do that, if I place an object here close to that, immediately the rays will, you can actually do ray tracing and see that the rays will travel in this fashion. The moment they hit this positive and negative index material interface, they bend backwards, and similarly this bend backwards, and the waves are focused in the negative index medium. Okay. And what will be the focal length? Well, it's simply going to be the opposite of it, right? So basically the focal length is going to be F here. And now if my thickness is D, this distance is going to be my D minus F. Okay. And so this distance at the waves will propagate back, and then you should actually have again D minus F. At a D minus F distance, the waves will converge back. So basically you get an image of the object here at this side. I'll have to verify whether it is, F. So this must be D minus F, I guess. It's a negative index, and the same so I think this should be fine. Let's see. Yeah. So all right. So you have a negative index here, and then it's converging back. So this is basically a lens which images, and the total distance between these two objects, if I call this as an object and the image, this distance is going to be 2 times D. Yeah. The total distance is going to be 2 times D. So when I have scenario like this, the interesting feature that Pendry said was, this is a perfect negative index medium. What do you mean by that? This has mu equal to epsilon equal to -1. When I have such a scenario, Pendry showed that, the impedance of this medium is going to be simply, I think it should be mu on the top. So mu times mu naught divided by epsilon times epsilon naught. Okay. When both mu and epsilon are negative, we can see that the impedance is basically going to be the free space impedance. So the negative index medium is perfectly impedance match. Negative index medium is perfectly impedance matched. What this means is, reflection is going to be 0, and the transmission through the material is going to be given by exponential k times the distance d. So what you'll see is, if you have such a negative index medium and have an object, as you go away from the object, the evanescent wave decays, but the moment it enters into the negative index medium, the evanescent wave grows in amplitude. So evanescent wave you remember what is evanescent wave? So we said that there are certain frequencies which cannot be supported by the medium, so the wave vector essentially becomes imaginary, and so that component of the wave vector, or that component of the image decays, right? But now if you have a negative index, the phase velocity is going to be opposite, and it turns out that we can actually show mathematically also that the transmission, the evanescent wave is getting amplified inside the negative index medium, and then after that again it decays. Eventually you get the same amount of information as was there as an object. So the perfect lens, which is simply a slab of negative index medium, can actually perfectly image an object. Now this was a big claim, and that's why people were very excited, because all the lenses that we have are diffraction limited. We are losing the evanescent wave, and because of that the resolution is limited. Now the claim is if you make a negative index material, you can actually have completely no diffraction limit at all. You should be able to image objects perfectly. The only problem is this sort of a negative index. It's very, very susceptible to the surface roughness and then the material variations, and also it is not possible to have negative index at all frequencies. We saw that we need to engineer a resonant response. If you have to engineer a resonant response, then you're going to have a very narrow region, like what we showed in the previous lecture. The negative index can be engineered only in very narrow regions. So it becomes very challenging. Even the losses are going to distort, and eventually the performance of the perfect lens is going to be limited. But it is a sort of a idea that was very captivating. All right. And Pendry also recognized the limitations of the perfect lens, and so he made one more proposal, what he called as a near field superlens, or a poor man's perfect lens. That's what he said. So what he said was, okay, fine. I mean, a perfect negative index medium is ideal, but it's not possible. So even if you take just a medium with epsilon equal to -1, a silver slab, right, with epsilon equal to, in this case, -1, if I take and I place that, and I have an object and then an image of some distance, let's say d. This is again my d, right, the thickness of the slab, and this is going to be my 2d, the distance between the object and the image planes. Okay, even this slab can actually help me image very well. Okay, but it only works in the near field. What do we mean by near field? Well, if I'm using lambda equal to 365 nanometers, the near field is tens of nanometers. Beyond that, it becomes technically beyond a distance of lambda away from the object is known as far field. Okay, but in this case we want to be in the near field. If you have such an object, like he considered the case where there are two objects like this spaced apart at a distance of, let's say, I think he considered to be 40 or 50 nanometers or so. So he had this object, he put them in this and then simulated what happens in the image plane. If it's an ideal lens, you should get a object faithfully like this. But if you just, without any object, you propagate the object in the space and then look at the image plane, you will see a kind of completely broadened shape light that comes in. That shows that you are not able to resolve these two objects. But the moment you put a silver slab, you see that the intensity is like this. So essentially we are able to see distinctly that there are two objects. There is some information lost, otherwise you will not have this broadening. You will have a perfect, it's not a perfect lens, but still you are able to resolve. And you are able to do it in near field. Okay, so this was a poor man's super lens, or poor man's perfect lens, and he made this proposal in the same paper, and quickly enough people were trying to do it. And then in the year 2005, from Shangjiang's group, they showed this experiment wherein they considered the slab and then they put chrome layer, and then they fabricated gratings. For example, this was, I think, grating with a pitch of lambda by 6. In this case, they used the illumination of 365 nanometers, and then they had a grating of lambda by 6, and then also they had some objects with 40 nanometer feature sizes. When they did this and they illuminate that object, you see that it propagates in a medium. This thickness is going to be my spacer, and then this is my near field super lens. Okay, NFSL, near field super lens, and then in the photoresist on the top, they were actually able to image the object, and that's what is shown here. So you have the object, you have the near field super lens, and this is the image plane, and what you're able to see is with 365 nanometer light, we are able to image objects which are size of 40 nanometer features imaged faithfully. If you look at the traditional diffraction limit, you would say that, 365, so maybe lambda by 2 roughly, I should not be able to image, but in the near field they're able to do it, and this sort of is a way to beat the diffraction limit, and there was this excitement around that. All right. So this was, at least in the early 2000s and, till up to 2012 or so, this was a very interesting area. There was yet another proposal, this time from Evgeny Narimanov's group at Purdue. So what they said was, the origin of diffraction limit is basically that the higher spatial vectors are not, k vectors are not able to propagate. So what they said was, if you take a regular medium, isotropic medium, we already saw that kx square plus ky square is going to be equal to omega square by c square. If I have a medium, I'm going to put again, there's going to be an n. N is essentially root of epsilon. So n square will be epsilon. So if I have any other medium, I can say epsilon, divide by epsilon. This is my dispersion relation. And if you look at this, if I plot this in the kx and ky and kz plane, this turns out to be a sphere like this. So this is my isofrequency surface. Isofrequency surface. Now, this is with the regular materials, but with our knowledge of, let's say, the metal dielectric slabs, we saw that we are able to get anisotropic surfaces, right? Anisotropic media, right? So in principle, I can also have an anisotropic medium, wherein my dispersion relation becomes kx square divided by, let's say, epsilon y plus ky square divided by epsilon x. Okay, I am not explaining to you why this comes out, but just trust me, it comes omega square by c square. So when I have two different anisotropy, basically my refractive index is going to be different in the x and y directions, is what I'm saying. I mean, you can even put z direction, it doesn't really matter. So if you have this sort of an anisotropic medium, then your isofrequency surface becomes an ellipse. It's no longer a circle. Well, okay. It's no longer a circle, but it becomes an ellipse. And if one of the epsilons is negative, for example, I have an effective negative, let's say I make this as negative. Okay. If one of the permittivities is negative, we get what is known as a hyperbolic metamaterial, okay, or implies hyperbolic dispersion. What it means is that the isofrequency surface now, in the case of the regular medium or an isotropic medium, the isofrequency surface is bounded. That means all the k vectors that fall within that they can propagate. Whatever is outside cannot propagate. So we have diffraction limit. But the moment if one of these things becomes negative, then the isofrequency surface is hyperbola, and this keeps extending up to infinity. So in principle, you can have very, very large k vectors that are supported in such a medium. Okay. So if you have a hyperbolic medium, large k vectors or spatial frequencies, high spatial frequencies can be supported. So what, if you are able to support high spatial frequencies, well, the high spatial frequencies have the sharp information, right? The sharpness of the object is defined by the high spatial frequencies, and if we are able to carry them, we can actually go beyond diffraction limit. And so how do we create this, 1 epsilon negative, 1 epsilon positive? We talked about the metal dielectric slab, and then you are able to engineer the metal and dielectric, right? So it turns out that what Evgeny Narimanov's team presented was, if you have an alternating layers of metal and dielectrics in a circular fashion like this, in a spherical fashion, and you put two objects at the center, they will the information or the energy from there will propagate and then go in this along the radial directions, and eventually you will see that this can be magnified. This was a very, very small object, but depending on the radii of the inner and outer radii of this sphere, you can actually magnify it, and the information can be magnified and eventually imaged using a traditional microscope. So you don't have to worry about the diffraction limit anymore. All the high spatial frequencies are getting converted into propagating waves after they propagate through this hyperbolic metamaterial, which they called it as hyperlens. And quickly enough, of course, in by 2007, I think this was Berkeley team again, they demonstrated the hyperlens, wherein they imaged this object, which I think is, roughly about 20 nanometers, 30 nanometers or so, this ON. They were able to image using this structure, which was fabricated using alternating layers of metals and dielectrics. So I think they took silver and silica layers, alternating layers, and they were able to image that with that, they were able to show that you can actually image much below diffraction limit. And it was a very fascinating idea. You just have whatever nanoscale images you have. Let's say I'll put some dye, whatever, or bacteria or whatever, even viruses, small objects on this. And then they will basically, the high spatial vectors will travel through this, and then you can image them using a conventional lens. The only problem is how to create low loss metamaterials. It becomes very, very tricky. If you want to do it in the visible domain, the thicknesses have to be roughly in the range of tens of nanometers. So yeah, this is silver alumina multilayers. Yeah. So you have to have structures which are very, very uniformly done in the scale of nanometers, and that becomes a nanofabrication challenge, and because of which to some extent this research domain, this direction of creating lenses using negative index material has stalled for a while. If you look at the historical trends, it turns out that there are times when you make a lot of leaps, and then after some time it takes a while for a next leap to come because the technology is still limited. So right now, I think if there are any ways of actually making these alternative structures with very, very low roughness and low loss, I think there are revolutionary applications. But right now, I think still people are looking at, what else can be done. Right now, the focus, I would say, has shifted slightly from these, bulk metamaterials to what are known as metasurfaces. Those are actually much more easier to fabricate. And in the last 10 years, I think a lot of emphasis has happened on the metasurfaces. And that's what I will talk about in the next couple of lectures. And with that, we'll close this week's discussion. All right. So this is about the fascinating domain of negative index materials. The research was undertaken in around 2000 to 2010. That was the peak of this research. All right. So thank you very much for your attention. I'll see you in the next lecture where we'll talk about metasurfaces. See you. Bye.